Now let us consider the differential equation given on page 10 of your notes for chapter 1. And this deals with the idea of separation of variables. Now, this is another solution procedure or another method for us to solve a differential equation. Now, the beginning stages of this method is for you as a mathematician to ascertain whether this equation here can be separated in terms of its dependent and independent variables, as well as these differentials, which are also called rather the infinitesimals, right? So is it possible for me to separate the independent and the dependent equations and isolate them on either side of the equation, such that I have the independent variable x and the differentials of x on one side, and the dependent variable y and the differential y on the other. Okay, and so that institutes step 1. That's what we're going to start by doing. So step 1 involves, I'm going to write that down. So step 1 involves decide if we can use separation of variables. Okay, and what we mean by that is, can I separate the dependent and independent variables with its associated infinitesimals? Okay, and infinitesimals is another word for these differentials. Okay, so let us see if I can actually do that. Is it possible for me to do that? Okay, so I can say dy by dx is equal to 2y plus 3, and if I divide both sides by 2y plus 3 and bring the dx over, then what I get is this. Okay, that is what I get, and it's clear to me now that I have the dependent variable on one side, right, 1 over 2 plus y, and its associated differential, and on the right hand side I have the differential of x and its associated independent variable, which in this case is just 1. Okay, so is it possible for me to use the method of separation of variables? Meaning, was I able to separate x and y with its differentials? And the answer is yes, right? The answer is yes, I can do that. Okay, so I can use separation of variables. Okay. Now that we have decided that separation of variables is a viable solution method, we now need to find what is the function. Okay, so the problem now is, what calculations can I do so that at the end I'm able to find a value for y. Okay, I'm able to solve the differential equation for y in this case. Okay, so the first step that we need, or the next step rather, that we need to do is, in order to get rid of these differentials, now, what I do is I integrate both sides. So step 2 involves integrating both sides. Okay, and it's clear that I'm going to integrate the right hand side with respect to y, and I'm going to integrate the left hand side with respect to x. Okay, and then now it goes back to what I've mentioned already, and that is that you need a clear understanding of the rules of integration. Okay, and so here this is clearly an aspect of the integral of 1 over x, which is ln x, but here you can use integration by substitution. Okay, so here you can use integration by substitution in order to find what this integral is. Right, and if you do so, you'll find that this integral is a half ln 2y plus 3. Okay, that's the integral of 1 over 2y plus 3. And on the left hand side, or on the right hand side rather, we have x, and we have plus some constant k. Okay, technically I have added a constant onto the left hand side, but when we talked about constants, we talked about the idea of constants being arbitrary, and so this constant can be absorbed by this constant k. Okay, now what's left to do is to figure out how do I get from this step such that I'm left with y isolated on its own. And that involves a little bit of algebra. Okay, and so the first thing that we need to notice is that I can take this half over to the other side. Okay, first thing I can do is take the half over to the other side, and so I'm going to do that, and that gives me ln 2y plus 3 is equal to 2x plus k. Right? Technically, what I'm saying is that I can multiply this k by 2 as well. Right? If I take the 2 over, I should be multiplying it by the x to get 2x, and multiplying it by the k to get 2k. But again, this constant is arbitrary. Again, the constant is arbitrary, so 2k is just the same as k, because those are that constant rather is arbitrary. Now what I can do is I can raise both sides to the exponential function. And once I do that, I understand the concept of the natural log and the exponential function being reciprocals. So what I'm left with on the left-hand side is just 2y plus 3. And what I'm left with on the right-hand side, by the rule of exponents, I can split that exponent, and that exponent becomes e to the 2x multiplied by e to the k. And then at this stage, what I can do is I can make y the subject by saying y should equal to e to the 2x multiplied by e to the k minus 3, and all of that is divided by 2. Okay, now if I look at that, what is interesting there is that I now have some e to the k, and I have that number all divided by 2. So let's write that separately. I'm just going to write up top here. So I have y equal to e to the k divided by 2 multiplied by e to the 2x minus 3 over 2. Now, again, we go back to the idea of an arbitrary constant. We have Euler's number, which is a number, raised to k, which is another arbitrary number, divided by 2. So this entire coefficient here, which is just an arbitrary number, I can call that some other constant, a, multiplied by e to the 2x, subtract minus 3 over 2. And that is the solution for y. And so we've now systematically used the method of separation of variables to solve that differential equation. I'm going to leave you with one question, and the question is, can I use the method of direct integration for this question? And if not, why not? If so, why can we do so? And we will answer that question in the next lesson.